Welcome to the next video in measure theory and probability. This is video 4 discussing positive measures. And this corresponds to part 1, chapter 1, section 2 of the textbook. Now, I have laid out that one of our primary goals is to invent this notion of a measurement system for sets of real numbers, which is consistent with interval length. But we will often present definitions that are more general than that, because although that is like a primary goal, it's not the only one, and especially because we're going to generalize this to probability theory, so that's not necessarily always going to be intervals of real numbers and so on. So anyway, so we're going to present the notion of a measure function in more generality than we need for that specific goal of measuring sets of real numbers. And so let's start with a measure space. Now, by calling that a measure space, all we mean is that E is any set and this script A is some sigma field on E. Now let mu be some function from A to the interval from 0 to infinity closed. And we are going to define what it means for this function mu to be a measure function. Now, the first thing that it must have in order to be a measure function is that it should assign the empty set measure 0. And the second thing that it should have is sigma additivity. Let's talk about what that means. Now, if you have any countable sequence of measurable sets, and keep in mind, as we've said before, what that means by calling them measurable is that they are elements of our sigma field. So this is a sequence of measurable sets, and moreover, let's assume that they are disjoint, meaning that if you take any two distinct sets, their intersection will be 0. So we have this sequence of disjoint measurable sets. And what we're going to talk about is the measure of their union. And I am sure that plenty of people seeing this are wondering, why have I written a square union symbol here? Well, so the square union symbol means exactly the same thing as the union symbol, in the sense that, if I replace this with the regular union symbol, it would mean exactly the same thing. It would, right? This thing would be exactly the same set. The only difference is that we use a square union symbol when the sets are disjoint. Now, that might seem a little bit silly. I mean, why would you have a whole symbol that means exactly the same thing, and you just use it in this kind of like special case? Well, it is kind of a reminder that the sets are disjoint, and that is important. That's often valuable because this sigma additivity rule requires a disjoint union. And you can really get yourself into trouble by trying to apply this rule when your union is not of disjoint sets. And so it's nice to have this reminder, right? I mean, it's kind of nice to just always make sure that you check that the sets are disjoint and that you kind of bake it into the notation. It's a nice feature, at least I like it. Not everybody uses it, but I like it. So I'm going to use the square union symbol to denote a disjoint union. And so sigma additivity says that whenever you take the measure of a disjoint countable union, that you could get the same thing by instead summing the individual measures of each individual set. So that is sigma additivity. Now, if mu has all of those properties, it is called a measure on the measurable space, right? So EA was a measurable space. And moreover, the triple EA mu is called a measure space, right? So there is a measurable space. That is this here. It does not yet have a measure. Once it is furnished with a measure, we call it a measure space, right? So there's a measurable space and there's a measure space. Okay, the last thing to talk about here is this total mass of mu. That is what you get when you take the entire space, and remember, E is the universal set, so we're talking about measuring the entire universe. And whatever you get for that is called the total mass of mu. This actually has some interesting examples. Now, if we think about interval length, then we would be talking about measuring the entire real axis and assigning it its length. I think it's completely obvious that we would call that infinity. So there's an example where the total mass of mu is infinity. But there's an important example where it's not infinity, and that's when the total mass is 1. That is essentially a probability space, right? We haven't yet built up enough to really talk about probability connections just yet, but it's nice to see these little hints and connections even before we're fully there. Probability is going to be one particular kind of measure, and so we will take events, and the measure of the event will be the probability of the event. And if you measure the entire space, it's sort of a commonly encountered thing in a statistics or a probability class that when you measure or you take the probability of the entire universe, it must always be equal to 1. So there's the notion of the total mass of mu. Okay, let's now state some properties of measure spaces, and we will prove them down below. So let's start with this measure space that is EA mu, and let's also have a couple measurable sets, A and B. And now we're going to make the following claims. If A is a subset of B, and by the way, I think I meant to say this in a previous video, but I forgot. I am so used to writing a subset with the horseshoe and the underline, and that's the relatively more common modern notation. I think this is somewhat older notation, but the book uses it, and I'm going to try to match the style of the book, so I'm going to try to remember to write my subsets with the simple horseshoe just to match the book, but I know that since I'm so used to writing it this way, I'm often going to kind of revert to that way of writing the subset sometimes, but they mean exactly the same thing. Anyway, if A is a subset of B, then the measure of A is less than or equal to the measure of B. I think that's a very intuitive claim. If, moreover, the measure of A is finite, because after all, these measures can all be infinity. So if the measure is finite, then we get this property. Actually, it's nice to know the names of things whenever possible. And I believe this is called excision. I think I've spelled it correctly, although I'm not perfectly sure. But in any case, this is called excision. And it is the principle that the measure of B minus A is equal to the measure of B minus the measure of A. And it is important that this is only applicable when the measure is finite. So, there are examples where the measure is infinite and this equation is not correct. In particular, right, you can kind of always tell when there's something to worry about with infinity because it has to do with minus, right? In effect, you could run into a case where the measure of B is infinity, the measure of A is also infinity, and then you have infinity minus infinity, which is not well defined. So that's often a signal of where it can really be important that your measures be finite in certain cases. But I guess notice that this part of it does not matter whether anything is finite. That would be true even if all of these measures are infinity. Okay, let's move on to property 2, which says that the measure of A plus the measure of B is the measure of the union plus the measure of the intersection. Now, for this one, let's notice that it looks very much like a well-known probability law, which says that the probability of the union is probability of A plus probability of B minus the probability of the intersection. And if you took this term and moved it to the other side, you would get, and switch your probability to a measure mu, you would get exactly this equation. So why have we done this, right? Why have we taken this familiar probability law and rewritten it in this way? Well, it's because, again, there's some worry about having infinity minus infinity if we were talking about measures, right? For probabilities, that's not a concern because the measure of the entire space is 1. All these probabilities are going to be between 0 and 1. And so when in the probability setting, this is no problem at all. This is a great way to write things. But when you're in the measure setting, you really want to prefer to write things with addition because things come out cleaner because, again, you don't have to wrestle with the sort of caveats that have to come with saying something about infinity minus infinity. So that's why in the measure setting, we've written it this way. Okay, these get increasingly complicated and increasingly difficult to prove. This one is called continuity from below. And so let's start with a sequence of measurable sets, and in particular, this is going to be an increasing chain of sets. What that means is that each next set is a superset of the set that is below it. So what you want to kind of imagine is that maybe you've got like some set A, giving kind of a rough diagram, and then there's some set A2 and some set A3 and so on. And maybe like as this goes on and on and on, maybe they kind of eventually stabilize in some sense. That's at least a relatively interesting case. But in any case, right, so there's this increasing chain of sets. And what we're interested in is taking the measure of the union of all of these sets. And here we are not talking about a disjoint union, so I have not written it with a square union symbol. And the claim is that in this case, you get the same thing if you take the limit of the individual measures. Now, you might be wondering, what is this up arrow in my limit expression? That is very similar to the square union symbol in that if I deleted it, it would not change the meaning, right? So it does not mean something different from the limit. It just is still talking about the limit. But we write an up arrow when the sequence of real numbers is monotonically increasing. So again, this is just notation that's kind of a reminder of some of the features of the stuff that we are working with. In this case, saying that the sequence is monotonically increasing. Why would we want a reminder that this sequence is monotonically increasing? Well, especially, first of all, just recall that there is this well-known theorem from real analysis which says that if you have a monotonically increasing sequence and it is bounded above, then the limit must exist. Now, that already makes monotonically increasing sequences worth clocking, like is it a monotonically increasing sequence or not? But more than that, not only if it is bounded, then it must have a limit, but if it is unbounded, then it just goes off to infinity, right? A monotonically increasing sequence, what it can't do is oscillate up and down and fundamentally have no limit whatsoever, right? So it either approaches some finite value or it goes off to infinity. Well, for our situation, now that we're talking about infinity like it's a true number, then we can simply say the limit exists because even if it goes to infinity, we would now regard that as just another case of the limit existing. So for us in this class, if a sequence is monotonically increasing, whether it is bounded above or not, the limit always exists. And that makes it especially nice to remember or note when sequences are monotonically increasing or decreasing. So anyway, there's continuity from below. Now, why is it called continuity from below? I think the from below part is relatively easy to understand because we are starting from a small set and getting a bigger set and a bigger set. And if this does in fact converge to something, then it seems to do so from small to big, so it's, from below. So I think the from below part makes good sense. Why is it called continuity? Well, an important real analysis fact that I feel in some analysis classes is not sufficiently emphasized is that continuity is in fact about, or basically the same thing as, the ability to move a limit from the outside of a function to the inside, or vice versa. So this equation here, with appropriate provisions about exactly what this xn is and blah, 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 but this is just a kind of quick, rough picture of what continuity really means, or not what it really means, but at least one way of viewing continuity, right? This function f is continuous if this equation is correct for every possible sequence that converges, blah, blah, blah. But anyway, so that's, that from a certain perspective, that's what continuity is all about, is the ability to move inside or outside as you wish, the limit. Well, so how does that apply over here? Well, this thing over here, this infinite union, is a lot like having your limit on the inside of your measure function, so that, so that it's a bit like this. It's not a literal, it's not like a true one-to-one kind of version, because this is not truly a limit in the same sense as it is for real numbers, but there's a very strong analog, right? This is a lot like doing something and taking it to the limit. So anyway, so this left-hand side is like having a limit on the inside, and the right-hand side is clearly having a limit on the outside, so that this property says that the limit can move outside the function, and that is basically the notion of continuity. Okay, we also have continuity from above, and unsurprisingly, it's very similar. We have a sequence of measurable sets. We have a chain, meaning, but this time this is a decreasing chain, meaning that each next set is a subset of the previous set. Now for this version, we need the extra condition that B1 is finite. But when we have all of this, then somewhat unsurprisingly, we say, we can take the measure of the intersection this time, and it is equal to the limit of the monotonically decreasing sequence of mu bn's. Okay, and then finally, we have this property, which says almost exactly what sigma additivity says, except that we will not assume that the sets are disjoint, so I'm writing a regular union symbol here, and because of that, we cannot say an equal sign here, but instead we can say a less than or equal to. Now, I do want to sort of argue that this sort of result makes some decent intuitive sense. So imagine that you took an interval from 1 to 4, let's say. And then here, let's say that we go from 3 to 8 or something like that, okay? So we have one interval here going from 1 to 4, right? And then the other interval is here going from 3 to 8. Now, if you were to measure the union, right? The union would just be the interval from 1 to 8, and it would have measure 7. But if you took these two pieces, right, the first piece would have measure 3, right, going from 1 to 4 has measure 3, or length 3. And then if you took it from 3 to 8, you would have length 5. And then when you add those together, you get 8, which is bigger than 7. So that is kind of a sort of simple geometric demonstration where the measure of the union here was 7, but the sum of the individual measures, because they had this significant overlap, the sum of the individual measures was bigger. Okay, so let's now prove these claims. So for the first one, now often what you want to do with these claims is to break your sets into disjoint pieces. Now remember what we're trying to prove in this particular theorem is we assume that A is a subset of B, and that means, right, like let's kind of think of it as a picture like this, And we want to carve this into disjoint pieces so that we can sort of say something about the measures of the pieces, right? Use that sigma additivity property. So how should we break this into disjoint pieces? Well, I think it kind of stands out as natural that A should be its own piece, and then you take everything that is left outside of that, which is essentially the same thing, as B minus A. So that's the first move that I make here, is I take my set B, but I break it into the pieces A and the disjoint union with B minus A. By the way, the fact that B is equal to a disjoint union B minus A, you should be able to prove that formally. Of course, it depends on the fact that A is a subset of B, but it might be a good exercise for you right now to just pause the video and make sure that you could formally prove that if you had to. In any case, the point of doing that is so that I can use sigma additivity and break up these measures, which is exactly what I do on the next line. Now, that's productive, but often with these proofs, we need to have kind of two cases, right? A case for the infinite situation and a case for the finite situation, because these measures can be infinite. And often you break them into those two cases because the logic of working with infinity is often different from the logic of working with finite values. So let's first consider the possibility that mu A is infinity. So if mu A is infinity, that means this term here is infinity. This term here is a non-negative quantity, and so when you take infinity plus a non-negative quantity, you get infinity, which is to say that this is all y. Mu b must be infinity in this case, and so we get mu b is infinity. Well, altogether then, that means that mu a and mu b are both infinity, they are equal, and therefore the greater than or equal to claim holds. So next, let's consider the possibility that A is finite. So if A has finite measure, then what we can do is actually take this term and subtract it to the other side. Now, if you think, like, why is that valid? Well, effectively, let's just think just to kind of summarize these things, let's say that that's X, that's Y, that's Z. We're talking about X equal to Y plus Z. And we know here that y is a finite value. Now, let's consider possibilities for z, right? If z is infinity, then you've got finite plus infinity, so x is infinity. Now, if you contrast that with what you would have in this equation, right, x minus y equal to z, again, you'd have infinity here, right, because that's what we were imagining. Over here, you'd have infinity minus this y, which is a finite value. So again, on the left-hand side, you have infinity, which is also true, right? So basically what I'm arguing is that when you have, right, like when we're working with infinities, this move is a valid move, right? Like the first one has just both sides equal to infinity. The second one also has both sides equal to infinity. So this move is valid when z is infinite. Now let's consider the case when z is finite. Well, if z is finite, you've got y, which is finite, z is finite. The sum of them is finite, so that means x is finite. We're now dealing with a situation where all of these quantities are finite. And we know that when they're finite, subtracting y to the other side is a valid move. So, in effect, what I have just done quickly is to try to argue that this move, this subtracting y to the other side, is still a valid move so long as y is a finite value. And that's why I get to do it here, right? So I'm basically using that principle to arrive at this equation. So I now have this equation, and by the way, this was one of the things that the property claimed, and I have now proved it, right? In the finite measure case, we have proved this equation, which was one of the things we were seeking to do. So that's great. But not only that, I also know that this right-hand side is a non-negative quantity, which is to say it is greater than or equal to 0. And because of that, I can now say that, this thing is greater than or equal to 0. I can add mu a back to the other side, and I arrive at this inequality, which is the other thing that we were trying to prove all along, so the proof is now complete. Okay, let's move on to the second property. And this is the property which claims that mu a plus mu b is equal to the measure of the union plus the measure of the intersection. Now, for this one, let's just immediately start breaking things into the infinite and the finite cases. For the infinite case, let's imagine that one or the other of these two measures, and it really shouldn't matter which one, right? There's a kind of obvious symmetry. Let's just suppose that one of them has measure equal to infinity. Well, if one of them has measure equal to infinity, then, no matter what the other one is, we know that it is non-negative, and therefore you do infinity plus a non-negative quantity must also be equal to infinity. And so this left-hand side is equal to infinity in this case. Okay, what about the right-hand side? Well, suppose, right, like if it were mu a that's infinite, then A union B contains A, of course, and therefore by the first property, we know that mu A union B would have to be greater than or equal to mu A. So ultimately what this tells us is that the measure of the union is infinity, and therefore this right-hand side must be infinity because it would be infinity plus a non-negative term. So there you have it. So what we have ultimately argued is that both sides of the equation are infinity in this case, and the claim is therefore correct, right? Because you get infinity equals infinity. Okay, so let's now move on to the usually tougher case where the values are all finite. So if measure of A and measure of B are both finite, let's think about how we're going to decompose these sets, right? We're going to, again, return to this idea that we almost always want to take these sets and break them into disjoint components. And we're going to work with this thing A union B. And, somehow relate it back to this equation eventually. But let's just, sort of look at this union because the union kind of has everything in it. So what are we going to do with this union? Well, I think it makes intuitive sense to just grab one of the sets, let's say A, picking somewhat arbitrarily, because I could have picked B and still done a successful proof. But let's select A and take that to be a whole piece that we're gonna kind of like cut out of the union. And then what's left over is just B without A, which is to say B minus A. So that's what I've effectively done in this first move, in this first equation, is take the union and cut it into A and B minus A. And of course, the point for doing that is always to apply sigma additivity, so we break up the measures into the individual pieces. But this does now leave us, or we have one thing that is good, right? The measure of A, we know that's part of what we want. But it does leave us with this thing we don't want, which is mu B minus A. Now, we know that we would like to have the measure of B instead here. So is there some way that we could obtain that? Well, often what you do in mathematics, like this is actually a fairly general trick, is that if you need some term, just include it, but then also subtract it back out so that you have balanced everything. But in this particular case, I need the missing piece, right? From the perspective of B minus A, the missing piece is this right here, which is the intersection. So I would love to give B minus A this missing piece so that we could be talking about the measure of B. I'm going to go ahead and give it that missing piece. I'm going to add in mu of the intersection. But to balance things out, I also have to subtract back out mu of the intersection. Now, I do want to point out while we're here that I can only do this move because the measures are assumed to be finite. If they were infinite, we might be looking at an infinity minus infinity case, and that is not defined. So anyway, because these are finite, I'm free to make this move. Okay, what I do next is I take these two terms, right? The plan all along was to take those two terms and merge them together, which is perfectly fine, right? We have sigma additivity. These are disjoint sets. In a sense, it kind of feels like I'm running sigma additivity in reverse, but really these equations don't have a direction, so I can run it in this direction if I want to. And of course, this term is eventually going to turn into mu of b, right? Because after all, the set inside there is nothing other than the set B. But I do still have this minus the intersection hanging out at the end. Well, all I do is I take it and move it to the left-hand side of the equation. So I now have the union plus the intersection equal to the measure of A plus this right here, which we already said is the measure of B. And that is exactly the theorem we were trying to prove, so the proof is now complete. Okay, let's move on to continuity from, from below. And so let's, again, immediately sort of break this up into an infinity case and a finite case. Here we've got this infinite sequence of growing sets. And so let's consider the possibility that any one of those sets, even just one of them, has measure equal to infinity. Well, if it has measure equal to infinity, then it is a subset of the union. The measure of the superset must be greater than or equal to the smaller set. So in this case, because we have infinity, this means that the measure of the superset must also be infinity. Okay, so that's the left-hand side of the equation that we're trying to prove. Recall that we're trying to show that the measure of the union n, right, this countable union is equal to the limit of the individual measures. And we've just shown that the left-hand side of that equation is infinity in this case. Now also, let's think about the right-hand side. And to show that the right-hand side is also infinity, notice that because we have this increasing chain, right? So an is a subset of an plus 1. And so that means that every set after this particular n, right, is a superset, and therefore its measure is equal to infinity. What that then means for us is that, so because every term after n is a superset, then therefore they all have measure equal to infinity. And so what that means is that eventually this sequence just turns into a constant sequence. And although you may not have really had a lot of practice with taking limits of things that have infinity in them, it makes good sense that we would just say that if, if the sequence becomes infinite, right, there's just a constant sequence of infinities, then the limit would be infinity. So that is the result here. So again, right, all together, we've shown that the left-hand side is infinity. The right-hand side is also infinity. So in this case, where at least one of them turns out to be infinite in measure, in that case, both sides of the equation turn into infinity. And the theorem is proved for that case. Now, let's start talking about the case where every single measure is finite. Okay, in this case, we're really going to need to do some work, and so we're going to break our sequence into disjoint components. Now, recall that we're talking about this increasing sequence, And so just to kind of give you a rough picture of that, right? So we've got A1, A2, A3, and they are getting bigger and bigger. And so if we want to cut this into disjoint sets, then it would make sense, right? Once you have A1, well, you just say, yeah, that's my disjoint set, so to speak. I mean, there's nothing to intersect it with, so in some trivial sense, it's disjoint. But when you get to A2, then you want to subtract away all the stuff in A1 so that you have a disjoint set. So what we're doing is defining a new sequence, C1, C2, C3, Cn, so on, Cn, such that these are now disjoint from each other. And in general, whenever n is at least 2, then we'll say that Cn is an minus 1. Now, by the way, not only are these sets disjoint, but they're also measurable, right? I claim that each Cn is in our sigma field. How do I know that? Well, I'm going to let you kind of do at least formalize the argument. It's a nice exercise, but I'll tell you roughly how that goes. If you have, right, we know that the sigma field is closed under complements and it's closed under unions. Well, that means you can take the complement of a union and get the intersection. Now, you have to be a little bit more precise about exactly how you handle that, but roughly speaking, you can show that a sigma field is always closed under intersections. So the sigma field not only is closed under unions, it's also closed under countable intersections. And then from that, you can expand this as basically being an intersect, an complement, and by closure properties, that must be in our sigma field. So again, I encourage you to actually formalize that argument, but it's not a hard one, so I'm leaving it as an exercise, and I've already kind of given you the outline there. So this is a disjoint sequence of measurable sets, and we have built it precisely so that we can use sigma additivity. Now, and by the way, not only all of that, but the two sets are exactly the same when we take their union, right? Like this has left nothing out, nor has it added anything in. So these are exactly the same set. So we get this equation. Then by sigma additivity, we get the next line. And then you think, well, what do I do from here? Well, it's probably a good idea to expand Cn into the difference of sets which it is equal to. Which is to say, we'd like to take Cn and replace it with mu an minus 1. Now, there is a little caveat, which is that A1 was defined differently, so we can't do that for A1, but that's no big deal. We just split that off from the summation, and we take the summation, right, for everything else, we can do this right here. Now, once we're looking at this, we might notice that perhaps we can use excision, right? We would maybe want to turn this into the measure of an minus the measure of an minus 1, and that hopefully looks a little bit provocative because that looks a whole lot like a telescoping series, which you hopefully recall from an earlier course in calculus or analysis. But, right, just to talk out how that goes, right, let's turn this into the limit of partial sums because, of course, that is what an infinite series is. And let's think about evaluating some mth partial sum. And if you evaluate this with n equal to 2, you get mu a2 minus mu a1. But then when you evaluate it with n equal to 3, you get mu a3 minus mu a2. And what's really magical about that is that these a2s cancel each other out. Okay, great. Now let's set n equal to 4. So we get mu a4 minus mu a3. And now the A3s cancel each other out and so on. Hopefully this is familiar, but this is the notion of a telescoping sequence so that you keep getting these cancellations until at the very end, the only thing that doesn't cancel is mu a m, right? Whatever was right before that will cancel, so that's mu a m minus 1. But in any case, so this mu a m survives, the minus mu a1 survives, and so that's what we have down here. Now, at this point, I'd like to push the limit into these two terms, right? I'd like to take this and distribute it here and here. I am justified in doing that. Why? Well, I know that this limit exists, and it exists because, as we've already remarked, this is a monotonically increasing sequence of numbers, and therefore the limit must exist. Also, the limit here must exist. And why does the limit here exist? Because that is a constant term, and because that is a constant term, then the limit of that sequence also exists. So since the individual limits exist, we know from analysis that we are free to push the limit into the difference. And that's what I have here for the first term, right? The result of pushing this limit to this term is exactly what I have here. Now, what about the second term? Well, when we get over here, the limit of this constant is, you just eliminate the limit, right? The limit of the constant is just equal to that constant, so you get minus mu a1. But we also have this mu a1 over here. They cancel each other out, and that's why they don't show up in the next line. Okay, so next let's talk about continuity from above. Now, we could produce a proof for this, which is very similar to the proof that we gave for the from below version. However, I am a big fan of taking things we've already proved and immediately turning them into tools that we use to make later proofs easier. And that's exactly what I would like to do here. It's a common sort of mathematical technique. And so I would like to prove continuity from above using continuity from below. But, okay, so continuity from below has to do with unions. What we have here is an intersection. Well, how are we going to relate the two together? I think it makes pretty good sense to use something like De Morgan's law, which says that if you take the complement of an intersection, you get a union. And in this particular case, it's going to be particularly convenient to try to situate everything inside of B1. So if we think like, okay, so here's B1, and then there are these smaller and smaller sets, and we are ultimately intersecting them. So there's B2, B3, and so on. And so we could talk about taking B1 minus this intersection. And you can prove, and I encourage you as an exercise to show that that is in fact the same thing as the union of all of these set differences. Moreover, this makes these set differences an increasing chain of measurable sets, and because of all of that, we therefore get to use continuity from, actually I think this is from below. Now, what continuity from below tells us is that if we take this union, which, I'm just going to use the fact that this union is actually the same thing as this set difference. So we take this difference. Continuity from below tells us that it's the same thing as this limit here. And now from here, we can use excision, and we know that that can be used, right? We always have to check that the sets all have finite measure, but because B1 has finite measure, then all the other sets must also have finite measure, and so we can use excision here. So we get excision, we distribute the limit, which we know we can do because this is a constant and this is a monotone decreasing sequence. And so therefore each limit individually exists, and that justifies distributing the limit to each of these terms. The limit of a constant is just equal to that constant, so we leave that there. And that is about as far as we can go along this path. But let's come back to the start where we said that we were talking about the measure of B1 minus this intersection. Well, we can also apply excision there. And so if we apply excision, we get that all of this is also equal to this thing down here. And there, the sort of like great reveal at this point is that this, right, in this equation, right, if we sort of isolate this equation, then we can cancel out the mu b1, we can cancel those two negative signs, and we get exactly what we were hoping to prove. Finally, we'll try to prove that the measure of a union is less than or equal to the sum over all of the individual measures. Again, we need to form a disjoint sequence. This time, we don't necessarily have a chain, right? We could have A1 is like that, and A2 is like that, and A3 is like that, and it can keep going and keep going. So how are we now going to build a disjoint collection of, or disjoint sequence of measurable sets? Well, as usual, right, when you have A1, it just makes sense to take A1 to be one of your, like just take it whole, right? Just take A1. That's disjoint in some trivial sense. But then for A2, yet again, we are going to just say that we're going to build this new sequence of C's, right? C1, C2, C3, and so on. And C2 will be A2 minus A1. Well, that's exactly like what we had before. But with A3, you see things become a bit different, right? We certainly will take A3 and we will subtract other stuff off. But we won't just subtract A2. Because if we merely subtracted A2, then we might, have overlap with A1. So we don't want to just subtract A2, we want to subtract everything that came before. And therefore, for each n, right, Cn will be An, but then subtracting off everything that came before. Now with this, we have a disjoint sequence of measurable sets, and it is perfectly equivalent to the original union. So we get that the measure of that union is the measure of the disjoint union of CNs. The whole point of doing all of that was to apply sigma additivity, which we have here. And then we can just use the fact that Cn is always a subset of An, and therefore the measure for An is always greater, in the weak sense, but always greater than or equal to the measure of Cn. And then we have just this real analysis sort of result or theorem that when you do a term-by-term comparison in the second series, every term has a greater than or equal to term compared with the first series, then the series have this natural relationship to each other. So this is kind of coming from basic analysis, this inequality. And there you have it. The theorem is complete, or the proof is complete.